At Tesla's Battery Day event, Elon Musk made a bold claim that raised more than a few eyebrows. He mentioned that there were batteries already in limited production capable of exceeding 400 watt-hours per kilogram, a density high enough to make medium-range electric aircraft a real possibility. At the time, many dismissed this as typical Musk hype. Ambitious promises meant more for headlines than engineering feasibility. But fast forward 5 years, and those words no longer sound like exaggeration. Instead, they read like a roadmap, a carefully placed marker for what would eventually shape Tesla's venture into aviation. The company's vision of a super-electric plane now revolves around delivering 400 miles of range with turnaround times as short as 12 minutes, something that once seemed impossible but is now beginning to look plausible. This vision comes together through a combination of advanced aerodynamics, distributed electric propulsion, revolutionary battery swapping methods, and fast turnaround cabin design. Taken together, these elements begin to paint a picture of how such an aircraft could actually operate day in and day out. One of the foundational aspects of achieving this range lies in the exterior design of the aircraft. Tesla's approach centers around a one-piece composite skin that drastically reduces the number of rivets and joints, resulting in a flatter, smoother surface with significantly less drag. On top of this, a hydrophobic nanocoating ensures that dust, water, and other small particles don't cling to the fuselage, preserving the surface smoothness and minimizing additional drag from roughness. In aviation, skin friction drag is a major contributor to overall resistance, often accounting for 40 to 50% of parasite drag in small and medium-sized planes. A slight reduction in this coefficient can translate into meaningful performance gains. Tesla's design promises a real-world reduction of 2 to 5% in drag, which, when linked directly to power demand, means a proportional extension in range without requiring a larger battery. The wings are designed to be long and slender, equipped with winglets to suppress vortex losses at the tips. Increasing the wing's aspect ratio from 10 to 14 can lower induced drag by as much as 30%, while winglets add an extra layer of efficiency with reductions of up to 10%. Retractable landing gear that seals flush into the fuselage further contributes to streamlining the craft, preventing unnecessary protrusions that act like bricks in the airstream. Even the maintenance panels and inlets are recessed and smoothly integrated, minimizing disruptions in airflow. These refinements, while individually small, collectively result in significant drag reductions, vital for an electric aircraft, where every % saved translates directly into more miles flown. Beyond aerodynamics, propulsion becomes the next defining piece of the puzzle. Tesla's electric plane is envisioned to use distributed electric propulsion, with multiple smaller motors positioned along the wings and paired with variable pitch propellers. This arrangement allows for airflow to be more evenly distributed across the wing, improving lift at low speeds and enabling shorter, safer takeoffs and landings. With this advantage, the aircraft can actually use smaller wings without sacrificing performance, reducing the wetted area and thus decreasing parasite drag. Variable pitch propellers keep each motor operating within its peak efficiency zone, regardless of changes in altitude or speed, squeezing out every possible percentage point of efficiency. In terms of raw numbers, the inverter may reach efficiencies around 98%, motors around 95%, and propellers between 80 and 88%, leading to an overall system efficiency of roughly 75 to 83%. By distributing thrust across many motors, each propeller spends more time operating in its sweet spot, which may improve efficiency by 1 to 3 percentage points. These gains are modest in isolation, but in an electric aircraft where margins are slim, they add up. The motors are also designed for direct drive, eliminating gearboxes that not only waste 2 to 5% of energy but also require constant overhauls. In addition, Tesla envisions the ability for regenerative braking during descent. Although this feature would only recover about 1 to 3% of flight energy, it can still provide power for onboard systems while extending the life of mechanical brakes, thereby reducing maintenance and downtime. The modular nature of the propulsion system also plays a role in reliability. With an N+1 redundancy model, the plane can continue flying safely even if a motor fails, as differential thrust from the remaining motors compensates. Each motor pod is hot swappable, and replacements can be performed in under an hour, minimizing ground delays. Combined with integrated sensors that monitor vibration, temperature, and current for predictive maintenance, Tesla aims for aircraft availability of over 99%, keeping fleets in the air rather than on the ground. Battery design and handling form another critical component of the aircraft's turnaround strategy. Rather than waiting hours for recharging, Tesla envisions a cassette-style battery system that slides in and out of the aircraft belly on rails, much like swapping out a giant power tool battery. With pack-level energy densities of 250 to 300 watt-hours per kilogram, each 1 megawatt-hour pack would weigh between 3.3 and 4 tons, necessitating robotic lifts or pallet trucks for handling. The swap process itself would take 6 to 8 minutes, broken down into positioning, unlatching the spent pack, and locking the fresh pack into place. This process avoids the need for extended charging sessions at the gate, as pre-cooled and pre-charged packs are prepared in advance. Still, fast charging is also an option, with Tesla designing the plane for nose-mounted charging ports that connect directly to high-power systems delivering between 2 and 5 megawatts. With liquid cooling integrated into the packs, waste heat from charging, ranging from 100 to 250 kilowatts, can be safely dissipated. Using quick coupler plumbing, industrial pumps, and carefully engineered coolant flow, the packs can be stabilized thermally within minutes of touchdown. A standardized connector interface across the fleet further speeds the process, with automated safety checks completing in under a minute before high-current charging begins. This ecosystem ensures that whether through swapping or ultra-fast charging, the aircraft can reliably achieve the promised 12-minute turnaround, an operational necessity for commercial viability. Inside the aircraft, Tesla has reimagined the passenger experience not only for comfort but also for efficiency. Boarding and deboarding traditionally consume significant ground time, often creating bottlenecks that slow operations. Tesla's solution involves dual doors and a straight aisle with a lower floor, allowing simultaneous entry and exit. Studies suggest this can reduce boarding times by up to 25%, potentially saving as much as 17 minutes compared to conventional single-door strategies. Cleaning also factors heavily into turnaround times. Standard narrow-body cabin cleaning ranges from 15 to 25 minutes, while optimized workflows can cut that down to around 6 to 10 minutes. Tesla's aircraft is designed with lightweight aluminum and composite seating, smooth upholstery resistant to stains, and simplified interior details that allow crews to wipe down and reset the cabin quickly. Seats themselves are significantly lighter, saving several hundred kilograms across the cabin, which translates into operational efficiency while also easing wear on brakes during taxi. Baggage handling is streamlined by shifting carry-on storage beneath the seats, reducing time spent rearranging overhead bins, a notorious cause of boarding delays. Overhead modules are heavy and cumbersome, so minimizing their number reduces weight while improving passenger flow. Maintenance-friendly cabin design further enhances efficiency, with quick-release floor panels and wall liners allowing for rapid replacement of high-wear parts without grounding the plane. This modular approach extends the aircraft's uptime, ensuring that even minor issues can be resolved without pulling the plane from service. Taken together, these innovations, from the seamless skin to the distributed propulsion, from battery swapping logistics to fast cabin flows, form a holistic vision for what an electric plane could look like in commercial service. Each improvement alone might save only a few minutes or a few percentage points of efficiency, but together they create a system capable of delivering 400 miles of range and turning around in just 12 minutes. What once sounded like marketing bravado now seems like a carefully engineered plan, a genuine step toward making electric aviation practical and competitive. If Tesla can deliver on this promise, it will not just reshape how we think about aircraft design but also redefine the expectations for speed, efficiency, and sustainability in the skies.